Greetings. My name is Tom Fay, and today I'll be sharing some history and technical insight into the revolutionary General Electric GE36 Propfan propulsion system of the 1980s. For marketing reasons, the Propfan engine is also known as the UDF for unducted fan, the UHB for ultra-high bypass engine, or more recently as the open rotor engine. As we'll see, a large publicly funded American initiative, the Advanced Turboprop program, produced two demonstrator engines, the single rotation ATP shown on the left and the GE36 engine shown on the right. I'll focus predominantly on the GE36 today. So why develop a Propfan engine? The driving force for this was the oil embargo by OPEC countries in 1973 and 1974, where the price of crude oil doubled in the course of a year. This had a huge impact on the American way of life, as well as the American economy, and measures were to be taken, including the speed limit, to reduce fuel consumption. A fuel efficiency gain of 30% for commercial airliners powered by just the JT8D jet engine would save 2.5 billion gallons of fuel per year. A Propfan is defined as a multi-bladed propeller with thin, highly twisted swept blades, which held the promise of greater fuel efficiency compared to propellers or turbofans. Why are the Propfans more fuel efficient? Thrust is a function of momentum, and for a given momentum, it is more efficient to move a larger amount of air more slowly than a smaller amount of air much faster. Momentum is defined as mass times velocity. However, the energy required to generate momentum is defined as 0.5 times the mass times velocity squared. To further illustrate this concept, here we compare two engines, a turbojet engine, which has no bypass functionality, versus the turbofan engine, which uses a fan to bypass some of the air around the core of the engine. You can see that both engines generate 200 units of momentum. However, the amount of energy to generate that momentum is halved for the turbofan engine. It is this fundamental concept that is the reason for the efficiency of the Propfan engine. The common index for expressing the fuel efficiency of a jet engine is known as the TSFC, or thrust-specific fuel consumption. It tells you how much thrust is generated per pound of fuel per hour. In this example, the pure turbojet, meaning all of the air is processed through the core of the engine, exemplified by the J47 of 1948, just over 1 pound of thrust was generated per pound of fuel per hour. The early turbofan engine, with a bypass ratio of 1:3, meaning 3 times as much air was accelerated around the core engine by the fan as went through the core of the engine, exemplified by the JT8D of 1980, offered a 27% improvement in TSFC versus the baseline turbojet engine of 1948. The high bypass turbofan, with a bypass ratio of 4:6, exemplified by the CFM56 of 1993, had a 59% improvement in TSFC compared to the baseline turbojet engine. And the ultra-high bypass engine, the Propfan, with a bypass ratio between 25 and 60, exemplified by the GE36 of 1985, held the promise of a 63 to 76% improvement in TSFC versus the turbojet engine of 1948. There were a number of significant unknowns facing the Propfan project in the late 1970s. First among them, would the propulsive efficiency predicted by computer models and wind tunnel studies accurately predict the performance of the full-scale article? Could the computer modeling accurately predict the acoustic behavior of the full-scale engines? Would the new generation of carbon fiber propeller blades be up to the task? Could these heavy, highly loaded prop fans be safely and efficiently integrated into existing or near future airframes? Could systems be developed such as engines, gearboxes, pitch change actuators, etc., be developed to support the promise of a prop fan? And last but not least, would the public accept the prop fan? To address these significant challenges, an alphabet soup of agencies and initiatives were undertaken to produce so-called enabling technologies that would support the development of the prop fan propulsion system. Under the umbrella of the ATP, or Advanced Turboprop Project, was the APET, which was a prop fan engine technology program, AGBT, Advanced Gearbox Technology Program, LAP, Large Scale Advanced Prop Fan Program, and then the PTA, the Prop Fan Test Assessment Program. These would assess noise and vibration issues, drive systems, installation aerodynamics, structures, acoustics, etc. A wide family of blades were designed, built, and tested in wind tunnels. Both single rotation propellers, SR, and contra-rotating propellers, CR, were investigated. The evolution of the blade shapes can be seen going from upper left to lower right, both for CR propeller blades, shown at the left, and the upper row towards the right of single rotation propeller blades. So why the interest in contra-rotation? Studies showed that a contra-rotating propeller could be 6 to 8 percentage units more efficient than single rotation. And this is a significant increase when tens of thousands of hours of engine operation are considered. It was very much worth pursuing. Before focusing on the contra-rotating prop fans, I wanted to show this 9-foot diameter, 8-bladed ATP propeller driven by an Allison D501 turboshaft engine, which was installed on the port wing of a Gulfstream II business jet exclusively for testing. The single rotation prop fan will be the subject of another video, but was a groundbreaking effort with resurgent interest in 2022 by Safran. Here's an abbreviated timeline of the Advanced Turboprop program. Proposed in 1975 and established in 1978, the first 10 years, 1976 through 1986, were spent on the development of so-called enabling technologies. In 1983, NASA contracts with Hamilton Standard and General Electric to build test rigs for the evaluation of both single rotation and contra-rotating prop fan blade designs. In 1983, General Electric stepped forward and proposed a gearless contra-rotating ultra-high bypass propulsion system, to which NASA and Lewis agreed to partner with GE, and that endeavor became the GE36 engine. 3 years later, in May of 1986, the GE36 first flew on a Boeing 727, and 1 year later, in May of 1987, the GE36 began flight testing on an MD-80 demonstrator aircraft. So this is the General Electric GE36 demonstrator engine. It's shaped like a football to allow smooth airflow into both the engine and the propulsor discs at all anticipated angles of attack. The engine was designed for efficient cruise at Mach 0.72 at 35,000 feet. The engine generated 25,000 pounds of static thrust at takeoff, and the fore blades work in an airstream slightly below Mach 1, while the aft blades work in an environment slightly above Mach 1. The unducted fan speed, that of the propulsors, is 1,390 RPM, giving a tip speed of 780 feet per second. For reference, the speed of sound is approximately 1,000 feet per second. The fan diameter is 11 3/4 feet, but the blades themselves are only 41 inches long. The weight of the engine is 8,600 pounds. There are 8 fan blades in each propulsor row, and independent RPM can be selected on either row. It is a gearless system. This is a schematic of the design of the GE36. A gas generator at the left provides a high energy gas flow to drive the turbines of the propulsor stages. The orange turbines, 6 stages, drive the rear propulsor, while the black propulsor is driven by the 6 stages of the black turbines. 6 stages for each propulsor was required to extract sufficient energy from the high-speed gas flow to drive the propulsors. The gas generator for the GE36 engine is a modified GE F404 turbofan engine, most commonly found in the F-18. It has 3 low and 7 high pressure compressor stages with 1 high pressure and 1 low pressure turbine. It has a bypass ratio of 0.34. The prop fan blade sets are 24 inches between centers, with modest differences in both sweep and weight between the fore and aft prop fan blades. The blades weigh only 22 odd pounds, which is key to managing the imbalances caused by a blade-off condition. Each propulsor rotor was independently controlled and capable of both feathering and reverse thrust. The red circles show where compressor bleed air was drawn off to both cool the mixer frame and to improve the stall margin of the propulsion system. The fan blades perform with a disc loading of 56 shaft horsepower per diameter squared in cruise flight and have activities of 147 and 152 for the fore and aft blades respectively. The targeted efficiency of the prop fan blades is 84.9%. The engineering challenges for the GE36 demonstrator were quite significant. First was the relatively low propulsor turbine speed of 1,390 RPM. Most turbines run at several-fold that figure. Because the turbines were driven by gas flow from the gas generator, dissipation of heat in the propulsor was a significant challenge. Unique to the prop fan, the prop fan blades had very shallow receptacles to accept the blades. Prop fan pitch change mechanism was also a challenge in being able to modulate the pitch of each rotor independently and rapidly. Harmonics between the propulsors and the airframe had to be managed, and of course blade-off integrity of the engine. The engine was designed to survive 1 blade off in each propulsor. This diagram shows the internal configuration of the GE36, showing the interdigitated contra-rotating turbines. The blue turbine rotated counterclockwise viewed from the rear, while the red turned clockwise. The inlet and outlet guide vanes are shown in green. The stages that carry the prop fan blades are termed power frames. There are no stators in the propulsor. Stationary structures are shown in purple, and the bearings are shown in yellow. The GE36 required 12 turbine stages of rather large diameter to extract the power required to drive the propulsors. The mixer frame, which mates the propulsor to the gas generator, was a structural masterpiece. It took all of the thrust and radial loads of the propulsor, all while channeling 1400-degree jet efflux into the propulsor turbines. Made of Inconel steel, it was perforated with 41,000 laser-drilled holes to reduce the gas temperature by 260 degrees Fahrenheit before it entered into the turbines. There are a lot of numbers on this diagram, But basically the gas flow enters from the left at 1200 degrees, expands and slows, exiting at 880 degrees. Note the temperature of the area sandwiched between the turbines and the cowling, or at the center of the engine, where around 600 degrees is experienced. Areas such as the blade bases and bearings are actively cooled by directed air. The primary source for cooling air for the propulsor was tapped from the bypass fan flow as well as from the compressor. Up to 19% of the gas generator inlet fan flow at takeoff was used to cool the mixer frame, pack the sump seals, and provide cooling air for the fan blade platforms and pitch change actuator, as well as the bearings. Unique to the demonstrator engine were telemetry modules that were very heat sensitive, and small angled scoops were put on the rotating fairings to cool these assemblies. Retention of the Propfan blades was yet another unique challenge presented by the GE36 design. A typical propeller blade has a socket that is twice as deep as it is wide. The GE36 was the reverse. The blades were slid into grooves of the red trunnion, and the red trunnion rotated on yellow bearings to adjust pitch. The trunnion was housed in the octagonal titanium support ring shown in green here. Blades could be changed with the engine on the aircraft. Each 41-inch tall blade generated almost 1,600 pounds of thrust. Because of the 12 large diameter turbine stages, the GE36 propulsor has over 1,000 blades in it. Amazingly, these blades were formed, brazed, and welded from sheet 3/100 of an inch thick. This design was found to be the lightest and most economical option, and the corrugated steel central stiffeners were tailored to tune the blade outside of resonant frequencies. Changing blade pitch on individual rotors spinning in opposite directions has always been an engineering challenge, even more so in an engine making 25,000 pounds of thrust with swept overhung blades. This was accomplished in the GE36 by a stationary concentric piston hydraulic ram located in the exhaust cone on the center line of the engine. Spider arms from the ram actuated multiple translation bearings, which slid fore and aft on internal stationary structure to link rods which rotated the blades on their axes. The blue piston actuated the blades on the fore rotor, while the red piston actuated the aft blade set. This was not an ideal design from a safety or redundancy viewpoint, but it did the job for the demonstrator engine. Many of these components were temperature sensitive and had to be actively cooled by directed airstreams. Initial flight testing took place with the GE36 installed on the starboard pylon of a Boeing 727-100 trijet. The port and centerline JT8D jet engines remained in place. Before flight testing, 100 hours of ground running was done with the GE36 mounted on the 727. Propulsor turbine blade fractures occurred, and this was traced to resonance caused by the airframe and the particular installation foibles of the GE36 on the 727. Damper pins were inserted between the blades on the susceptible stages. While this resulted in a loss of efficiency, it allowed flight testing to begin. Flight testing of the GE36 engine began on August 20th, 1986. Pitch, thus RPM, is independently controlled on each propulsor fan. However, for early flight testing, fan speeds on each propulsor and thrust loading were nominally set to the same value on each propulsor. Fan speeds could be synchronized and synchrophased to reduce vibration and noise. At the right are the details of the construction of the fan blades, where a partial length hollow titanium spar is covered with a bonded carbon fiber shell.
This unusual-looking jet engine has become the first of a new breed of aircraft power plants to take to the air. Called the unducted fan, or UDF, by its manufacturer, General Electric, the engine helped power a Boeing 727 on an early morning test flight August 20th at Mojave Airport in California. It was the first of a series of flights to be conducted by General Electric with participation by Boeing Commercial Airplane Company. The UDF is an example of what's known in the industry as an ultra-bypass engine, or Propfan. It's equipped with two large external fans that rotate in opposite directions. The fans are 11.5 feet in diameter and move a far greater volume of air for a given amount of fuel compared with today's conventional jet engines. That translates into significant fuel savings, which is why Boeing has selected this type of propulsion for its advanced 7J7 airliner due in 1992. The two fans are powered directly by non-geared counter-rotating turbines. The counter-rotating action allows the second fan to straighten the swirl of air caused by the first fan, and that contributes to the engine's efficiency. The 727 returned to Mojave Airport at the conclusion of the successful test flight.
Once the GE36 engine had passed initial flight testing, further work had already progressed towards choosing an airframe closer to what a commercial product might look like. This table presents some of the issues affecting the placement of a Propfan engine on a passenger airliner. The issues of acoustics, engine outperformance, interference drag, propeller inflow, and weight and balance are listed on the left, with 6 different installation options across the top. Excessive noise negated the mounting of the engines on the wings. Excessive weight prevents their mounting on a T-tail, and contraprops prefer clean air inflow to the fans. The aft pylon pusher and tractor configurations were the preferred options. The 140-passenger McDonnell Douglas MD-80 became the next test mule for the GE36 demonstrator engine. This is the GE36 timeline. As far as the 727 goes, 100 hours of ground testing had been achieved in July of 1986, where 25,000 pounds of static thrust had been achieved with an SFC of 0.24. Flight testing had begun in August of 1986, and all of the flying on the 727 was essentially complete by the end of 1986. By May of 1987, flight testing of the GE36 on the MD-80 aircraft had begun, and 165 flight hours had been accumulated by the end of July. In August of 1987, the GE36 was reconfigured to have 10 blades on the fore propulsor disc and 8 blades on the aft disc in an effort to reduce noise. There was little or no improvement in acoustic signature with this configuration. The following year, the GE36 was to return to the 8x8 blade configuration and flown over the Atlantic to the Farnborough Air Show in the United Kingdom.
General Electric's unducted fan engine, a revolutionary aircraft propulsion system, is now undergoing proof of concept testing. The two-stage counter-rotating unducted fan in this gearless system is directly driven by power turbines. The power turbine has 2 rotors. One is called the forward or outer rotor. The other is the aft or inner rotor. Each has 6 rows of blades. In a conventional power turbine, the forward turbine rotor would be stationary and simply guide the air into the rotating stage. After balancing, the rotors are assembled as a complete unit to form the propulsor. Each turbine rotor is supported by a separate rotating power frame. Polygonal rings assembled to the power frames provide for attachment of the fan blades to the power frame. The propulsor, less the fan blades, was assembled to the mixer frame, and the unit was prepared for shipment to General Electric's outdoor test site at Peebles, Ohio, for its initial test run. The unit was transported to Site 4A and mounted into the crosswind facility where the fan blades were installed. The position of each blade was calibrated and the variable pitch mechanism was checked out. In subsequent tests, the UDF demonstrated its ability to operate at full speed, and in a series of progressive tests, it has attained full power of more than 24,000 pounds thrust and an SFC of 0.24.
The flight test program is being conducted with a standard MD-80 aircraft, modified to accommodate engines in development by both GE and the team of Pratt & Whitney Allison.
Demonstrator. Basically a McDonnell Douglas MD-80 airliner, otherwise known as the MD-81. Just like the JT8P. Low speed pass at 160 knots. Head on, get away, turn away from you.
The Collier Trophy is awarded to the most significant advance in aviation during the previous year. The NASA GE PW Allison Propfan project was awarded the Collier Trophy for 1987. By 1989, the end of the American Propfan project had arrived. Crude oil prices had dropped to sustainable levels, and U.S. government funding of the program had ceased. Significant engineering challenges remained, such as noise to meet both present and future standards, safety, such as blade-off behavior and bird strikes, airframe integration, what aircraft could use this engine, reliability yet to be determined, the high installed weight, and the cost, both initial and operating, of the Propfan systems. In the meantime, advances in high bypass turbofan technology began to fill the efficiency gap. Data released only in 2011 revealed that GE, NASA, and McDonnell Douglas had been actively pursuing a commercial production Propfan engine at the time that the American Propfan projects closed. Research and design work resulted in Propfan blade designs that had advanced significantly since the F7A7 design had flown on the GE36 engine in full scale in both the 8x8 blade and 10x8 blade configurations. The flights of the full-scale Propfan demonstrators had confirmed the accuracy of computer and wind tunnel modeling with respect to noise and performance, and this provided the confidence to move forward with enhanced designs in a cost-efficient manner. The proposed commercial Propfan engine would use a 10x8 blade configuration with blade sets designated as F53A53. Here is a 1989 table of acoustic data comparing the flown 8x8 blade GE36 engine in red lettering versus the flown 10x8 GE36 in green. The proposed commercial Propfan units to be used in the MD-91 are shown in blue lettering and the MD-92 aircraft in the black bars. The MD-92 proposal was an option that used blade sets with higher propulsive efficiency, but also had higher noise characteristics. The blue horizontal bar is the acoustic limit defined by the FAR 36 Chapter 3 regulations, then in effect during the late 1980s. The first two panels show that both flown Propfan configurations of the 1980s exceeded lateral and takeoff noise standards. The third panel shows that all were acceptable during the approach phase to landing. Modeling of the MD-91 and MD-92 variants predicted they would easily meet the FAR 36 Chapter 3 regulations, and perhaps even future FAR 36 Chapter 4 regulations. But all of these plans were shelved with the termination of the Propfan programs in late 1989. This slide shows a data table with comparative data for the GE36 Propfan of 1988 compared to the CFM56 turbofan engine of the 1990s and the pinnacle of piston engine technology, the Wright turbo compound radial engine. For the same thrust, the Propfan used half the fuel, but weighed 3,600 pounds more than the turbofan. Note that the disc loading of the Propfan is 4.5 times that of the piston-driven propeller, which is testament to the advanced design and materials of the Propfan blade. Amazingly, General Electric made only a single GE36 engine throughout the whole program, and this engine now resides in the collection of the Smithsonian National Air and Space Museum. There was another Propfan engine of the 1980s, the Pratt & Whitney Allison 578DX. This was a geared Propfan engine, but that is a story for another time. Here is a listing of some of the references and sources for the information used to prepare this video presentation. Since the ATP GE36 program was a publicly funded program, there are excellent detailed documents freely available in the public domain. Please consider visiting the Aircraft Engine Historical Society website at the link shown here, and I thank you for your attention.